Representation Theory of Finite Groups, Lecture 25. Problem Session. Problem 1. Compute the Robinson-Shenstedt correspondent of the permutation with the one-line notation 283475196. So this is an element in S9. Solution. We follow Shenstedt insertion algorithm starting from the pair of two empty tableaus. Inserting 2 gives us the insertion tableau 2 and the recording tableau 1. Inserting 8 goes into the first row because it's greater than everything what is in the recording tableau in the first row. So we get the insertion tableau 2, 8 and the recording tableau 1, 2. Next we insert 3. 3 is greater than 2 but is smaller than 8. So 3 bumps 8 into the second row, and we have the running insertion tableau 2, 3 and 8, and the running recording tableau 1, 2 and 3. Next we insert 4. 4 is greater than everything in the first row of the insertion tableau, so it goes into the first row. So we get the insertion tableau 2, 3, 4 and 8, and the recording tableau 1, 2, 4 and 3. Next we insert 7. Again, 7 is greater than everything in the first row of the insertion tableau, so it goes into the first row. And we get the first row 2, 3, 4, 7, and then the second row is 8 in the insertion tableau, and the recording tableau is 1, 2, 4, 5 and 3. Next we insert 5. So 5 is greater than 4 but is smaller than 7. So it bumps 7 into the second row. So in the second row we have 8. So 7 bumps 8 into the third row and 8 goes into the third row. So we have new insertion tableau 2, 3, 4, 5, then 7 and then 8. And the new recording tableau 1, 2, 4, 5, then 3 and then 6. Next we insert 1. 1 is smaller than 2, so it bumps 2 into the second row, 2 bumps 7 into the third row, and 7 bumps 8 into the fourth row. So we get 1, 3, 4, 5, then 2, then 7, and then 8. And the recording tableau 1, 2, 4, 5, then 3, then 6, and then 7. Next we insert 9. 9, of course, is a maximal element, so it goes into the first row. It's greater than everything what is there. And so we just add 9 in the first row and write 8 in the corresponding box in the recording tableau. And finally, we insert 6. 6 is greater than 5, but smaller than 9. So it bumps 9 into the second row, and 9 is appended in the position 2, 2. So finally we have the insertion tableau of shape 5, 2, 1, 1, which has 1, 3, 4, 5, 6 in the first row, 2, 9 in the second row, 7 in the third row, and 8 in the fourth row. And the corresponding recording tableau is 1, 2, 4, 5, 8, 3, 9, 6, and 7. And this is our answer. The Robinson-Shenstedt correspondent of 283475196 consists of the pair of two standard tableaus of shape 5, 2, 1, 1, with the first one being 1, 3, 4, 5, 6, 2, 9, 7, and 8, and the second one being 1, 2, 4, 5, 8, 3, 9, 6, and 7. Problem 2. Determine the permutation sigma in S6, whose Robinson-Shenstedt correspondent is the pair of standard tableaus of shape 3, 2, 1, where the insertion tableau is 1, 3, 6, 2, 5, 4, and the recording tableau is 1, 2, 5, 3, 4, 6. So let us determine our permutation sigma using the two-line notation with the free slots in the second line. And we will solve the problem by reversing Shenstedt algorithm. At the first step of the solution, we look for the box which contains the maximal element in our recording tableau. So this is a box which contains 6. It's in the third row, first column. So this was the box which was last added in our insertion tableau. So we look at the corresponding box in the insertion tableau and we reverse Shenstedt algorithm. So we remove 4 from this box. It was bumped, so this 4 which was added in this box, it was bumped from the previous row. And what could have bumped it? It should have been 2, because 2 is the only element in that row which is smaller than 4. So 4 was bumped by 2, so we unbump it. So we replace 2 in the second row by 4. And now we have 2, which was bumped from the first row. In the first row, the maximal element which is smaller than 2 is 1. So we replace 1 by 2. And it follows that at the last step of Shenstedt algorithm, we were inserting 1 into this tableau 2, 3, 6 and 4, 5. So this means that sigma of 6 is equal to 1, and we have determined the last element in our second row of sigma. Okay, now we look which box in the recording tableau has the remaining maximal element, which is 5. So this is a box in row 1 and column 3. So now we look at our insertion tableau, which remains after we reversed the last step of Shenstedt algorithm, and the tableau which we had there was a tableau 2, 3, 6 and 4, 5. So if we now look at this tableau at what stands in row 1 and column 3, it's 6. So we remove 6 from this box. Since this was in the first row, it follows that at the penultimate step of Shenstedt algorithm, we were inserting 6 into the tableau 2, 3, 4, 5. Or in other words, sigma of 5 is equal to 6. So we have now determined 2 elements for sigma. Next step, we look at maximal box in the remaining recording tableau. It's 4 in position 2, 2. And now we have to look at the insertion tableau, which is 2, 3, 4, 5. We look at the box which is in the second row, second column. It is 5. We remove it. So this should have been bumped from the first row, and the element which bumps it is the maximal element in the first row, which is smaller than 5. This is 3. So we unbump it and get that sigma of 4 is equal to 3. Continue, we look at the element 3 now in the recording tableaus. In the remaining insertion tableau 2, 5, 4, it is 4, which is in column 1, row 2. So we remove it. It should have been bumped by 2 because 2 is smaller than 4 and 5 is greater than 4. So we unbump it and get that sigma of 3 is equal to 2. On the penultimate step, we look at the position of the maximal box 2 in our recording tableau. So this is row 1, column 2. In the insertion tableau, we have 5 there. When we remove it, we can now record that sigma of 2 is equal to 5. And the remaining entry is uniquely defined. So sigma of 1 is equal to 4, the only remaining element. So the answer is that the element sigma, whose Robinson-Shenstedt correspondent is the pair 1, 3, 6, 2, 5, 4, and 1, 2, 5, 3, 4, 6, is exactly the element 4, 5, 2, 3, 6, 1. Problem 3. Compute the evacuation tableau for the following standard Young tableau T of shape 3, 3, 2, 1, 3, 6, 2, 5, 7, and 4, 8. Solution. So we are looking for the evacuation tableau for T as the empty tableau of the same shape, 3, 3, 2. In step 1, we remove the northwest box from T, which contains 1, and we play jeu de taquin with respect to this box. So its east and south neighbors are 2 and 3. So 2 is smaller, so we swap this box with 2. The new box has 4 and 5 as south and east neighbors. So 4 is smaller, so we swap it with 4. The new box has only 8 as such a neighbor, so we swap it with 8 and we get a removable node. So in this position, in our empty evacuation tableau, we write 8. So this is the first step. And now we continue. So now we have this tableau, 2, 3, 6, 4, 5, 7, 8. We remove the northeast corner, which contains 2, and we place it in. The neighbors are 3 and 4, so we swap it with 3. The neighbors are 5 and 6, we swap it with 5. The only neighbor is 7, we swap it with 7. And so now we have the removable box in row 2 and column 3. So in our evacuation tableau, we write 7 in row 2, column 3. Next step, we continue with the tableau 3, 5, 6, 4, 7, 8, which we had at the end of the previous step. We remove 3. The neighbors are 4 and 5, so we swap it with 4. The neighbors are 7 and 8, we swap it with 7. And now we have a removable box in position to 2, so we write 6 in position to 2 of our evacuation tableau. Next step, we have the tableau 4, 5, 6, 7, and 8. We remove the northeast 4. The neighbors are 5 and 7, so we swap it with 5. The only neighbor is 6, we swap it with 6. And now we have the removable node in the first row and third column. So in the evacuation tableau, we write 5 in the first row and third column. Step 5, we continue with 5, 6, 7, and 8. We remove the northeast 5. The neighbors are 6 and 7, so we swap it with 6. And so we have the removable node in the first row and second column. So we write number 4 in the first row and second column. Next step, we have the tableau with 3 rows and 1 column containing 6, 7, and 8. We remove 6. The only neighbor is 7, so we swap it. The only neighbor is 8, so we swap it again. And we have the only removable node in row 3, column 1. So we write 3 in row 3, column 1 of the evacuation tableau. On the penultimate step, we have 7 and 8. We remove 7 and replace the empty box with 8. So we have row 2, column 1. We need to write 2 in row 2, column 1 of the evacuation tableau. And we have only one entry left, which must be 1. It is always 1. So the evacuation tableau is the following tableau of shape 3, 3, 2, which has 1, 4, 5 in the first row, 2, 6, 7 in the second row, and 3, 8 in the third row. Problem 4. Prove that the number of standard Young tableaus of shape n, n is equal to 1 divided by n plus 1 times 2n choose n. The easiest way to prove this is to use the hook formula. Here are the hook lengths for all boxes in the Young diagram of shape n, n. So in the second row, if we read from right to left, this is the last row, so the hook length simply increases by 1 on each step from right to left. So we start with 1, then 2, and so on, and the last entry is n. And in the first row, all hook lengths are exactly 1 bigger than the hook lengths of the boxes below them. So we have the hook lengths 2, 3, and so on, n plus 1. So by the hook formula, the number of standard Young tableaus of the shape n, n is equal to 2n factorial divided by n factorial times n plus 1 factorial. And if you move out 1 divided by n plus 1, we get exactly the formula 1 divided by n plus 1 times 2n choose n. Note that 1 divided by n plus 1 times 2n choose n is the nth Catalan number. Problem 5. Let sigma be an element in Sn, and assume that the Robinson-Shensted correspondent for sigma is the pair p, q of standard Young tableaus of some shape. Let sigma prime be obtained from sigma by composition with the elementary transposition I and I plus 1 on the left. So let the Robinson-Shensted correspondent of sigma prime be the pair p prime and q prime of standard Young tableaus. Prove that the difference between the number of rows in P and P prime is at most 1. Solution: the number of rows of a Young diagram is of course the height of the first column. And we have seen that the height of the first column in P is exactly the length of the longest decreasing subsequence for sigma. Similarly, the height of the first column in P prime is the length of the longest decreasing subsequence for sigma prime. So what we need to prove? We need to prove that if we swap I and I plus 1 in the second row for sigma, that this can affect the length of the longest decreasing subsequence only at most by 1. There are two big cases which we need to consider. The elements I and I plus 1 can be in the increasing order, which means I is on the left of I plus 1 in sigma, or in the decreasing order, which means I is on the right of I plus 1 in sigma. So we consider these two situations separately. First, assume that I is on the left of I plus 1 in sigma. Then any decreasing subsequence of sigma contains either I or I plus 1 or none of them. It cannot contain both because they are in the increasing order. So when we swap I and I plus 1, the following things can happen. It is possible that we remove this unique element from the increasing sequence, and then the length decreases by 1. It is possible that we replace the element by the other element in the decreasing sequence, in which case the length doesn't change. And it is also possible that we add the second element, because after swapping they now appear in the decreasing order, so they can appear both in the decreasing subsequence for sigma prime. So in this case, the length of the decreasing subsequence increases by 1. Note that we cannot add both of them to a maximal increasing subsequence because they are next to each other in the natural order of integers. So if after swapping them we add them both, then in the original sequence we could have added any of them and the sequence was still decreasing. So this is because they must appear next to each other in any decreasing subsequence. In the case when I appears to the right of I plus 1, in the one-line notation for sigma, a longest decreasing subsequence for sigma might contain both I and I plus 1 because they appear in the decreasing order. So let us swap an I and I plus 1 in sigma. So what happens with the decreasing subsequences? If it contained one of these elements, after swapping, we can replace it by the other one, and in this case, the length of the sequence remains the same. So if it contained both, then after swapping them, so they appear next to each other, after swapping them, they now appear in the increasing order, so the sequence cannot contain both, but we can keep any of them. So the length of the sequence decreases by 1. And the main point is that they always appear next to each other in the decreasing subsequence. So when we swap them, we can always keep one of them and still have a decreasing subsequence, which means that the length of the longest decreasing subsequence will not go down by 2. And this completes the proof. Problem 6. Determine a standard Young tableau T such that the evacuation tableau for T is the tableau 1, 3, 5, 2, 4, 7, and 6 of shape 3, 3, 1. Solution. Let sigma be an element in Sn whose Robinson-Shenstedt correspondent is the pair consisting of the evacuation tableau for T and T. Then we know that the Robinson-Shenstedt correspondent for the reverse of sigma is the pair of the standard Young tableaus, where the insertion tableau is the transpose of the evacuation of T, and the recording tableau is also the transpose of the evacuation of T. So let us determine this reverse permutation for sigma. So for this we need to reverse the Shenstedt insertion algorithm, and as we already seen, this can be done quite easily. So we look at the maximal box in the recording tableau. It's in the third row, second column. And now we reverse the insertion algorithm for the corresponding block in the insertion tableau. So it contains 7, we remove it. So this 7 was bumped by 4 from the second row, so we replace this. This 4 was bumped by 2 from the first row, we replace this, and we get that sigma reversed of 7 is equal to 2. So the next position in the recording tableau is 6 in row 1, column 3. In the insertion left over from the previous step, we have 6 in this position. It's row 1, so if we just remove it, we immediately get that sigma r of 6 is equal to 6. The next maximal block in the recording left over is 5, which is in row 3, column 1. In our insertion tableau, we have 5 in this position. We remove it. This should have been bumped by 3 from the second row, and 3 should have been bumped by 1 from the first row. So we have 1 as a leftover, which means that sigma r of 5 is equal to 1. So the next maximal box in the recording left over is 4 in position 2, 2. In the insertion tableau, we have 7 there. So we remove 7, and it should have been bumped by 4 from the first row. So sigma r of 4 is equal to 4. Next, we look at the maximal position 3 in the recording tableau. So this is box in the second row, first column. In the insertion tableau, we have 5 there. We remove it. It was bumped by 3. So we have that sigma r of 3 is equal to 3. The next position is 2 in the recording tableau. It's row 1, column 2. We have 7 in the insertion tableau there. So we remove it, and we have sigma r of 2 is equal to 7. And the last number is uniquely defined, so sigma r of 1 is equal to 5. So sigma r is 5734162, which means that sigma is 2614375. And now we can compute the Robinson-Shenstedt correspondent for sigma. So we start from the pair of empty tableaus. We insert 2 to get 2, 1. We insert 6, it's greater than 2, so it goes to the first row. So we have 2, 6 as the insertion and 1, 2 as the recording. Next we insert 1. 1 bumps 2 because it's smaller than anything in the first row. 2 goes into the second row. So the insertion is 1, 6, and 2, and the recording is 1, 2, and 3. Next we insert 4. Here is 4. 4 bumps 6 from the first row because it's greater than 1 but smaller than 6. And we have the insertion tableau 1, 4, and 2, 6. And the recording tableau 1, 2, and 3, 4. Next we insert 3. So 3 bumps 4 from the first row, 4 bumps 6 from the second row. So we have the insertion tableau 1, 3, 2, 4, and 6. And the recording tableau 1, 2, 3, 4, and 5. Next we insert 7. 7 is greater than 3, so it goes into the first row. So the insertion tableau is 1, 3, 7, 2, 4, and 6. And the recording tableau is 1, 2, 6, 3, 4, and 5. And finally we insert 5. 5 bumps 7 from the first row, and 7 is greater than 4, so it goes into the second row. So we have the final insertion tableau of shape 3, 3, 1, with 1, 3, 5 in the first row, 2, 4, 7 in the second row, and 6 in the third row. And the recording tableau is 1, 2, 6, 3, 4, 7, and 5. And now we see that the insertion tableau is exactly our original evacuation tableau for T, and then the recording tableau is our T. So answer is that T is equal to 1, 2, 6, 3, 4, 7, and 5. And finally, problem 7. Determine all partitions lambda for all positive integers n, such that the number of standard Young tableaus of shape lambda is equal to 3. Solution. The main observation is that a partition lambda with this property has at most 2 removable nodes. Indeed, if lambda has 3 removable nodes or more, then we can take a standard Young tableau of shape T, where the elements n and -1 and -2 occupy these 3 removable nodes. But then we can arbitrarily permute these elements and we will get standard Young tableaus. So we will have at least 6 different standard Young tableaus of shape lambda. Therefore, we have either 1 or 2 removable nodes. In the case if lambda has exactly 1 removable node, then it is of the form k, 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 k for some k. And if k is equal to 1 and the number of parts is equal to 1, then there is only one such standard Young tableau. If we have 2 parts of length 2, then we have 2 standard Young tableaus of shape 2, 2. And if we have 3 parts of length 2, then by the Hooke formula, the number of standard Young tableaus of shape 2, 2, 2 is equal to 6 factorial divided by 4 times 3 times 3 times 2 times 2. So these are the Hooke lengths. And this is equal to 5, which is greater than 3. And if k is greater than or equal to 2 and m is greater than or equal to 3, or the transpose situation, then we will clearly have even more standard Young tableaus. So none of these cases has the property which we want, which means that lambda should have exactly 2 removable nodes. So let us look at the situation when lambda has exactly 2 removable nodes. And then this means that lambda has a form k, 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 m times, and then a, b times, where a is strictly smaller than k. So here are some special cases. If lambda is 2, 1, then we have 2 standard Young tableaus. If lambda is 3, 1 or 2, 1, 1, then we have 3 standard Young tableaus for that shape. This is exactly what we wanted in the formulation. If lambda is 4, 1, then we have 4 standard Young tableaus of that shape. If lambda is 3, 2, then we have 5 standard Young tableaus for that shape. And if lambda is 3, 1, 1, then we have 8 standard Young tableaus for that shape. And these 3 partitions, 4, 1, 3, 2, and 3, 1, 1, these are exactly the partitions which are obtained from 3, 1 by adding an addable node. This means that in all other cases, our partition contains either 4, 1 or 3, 2 or 3, 1, 1 or their transpose. And hence the number of standard Young tableaus in that case should be at least the minimum of these 3 numbers, which is 4. This tells us that the answer to our problem is that the only 2 partitions for which the number of standard Young tableaus of the corresponding shape is 3 are the partitions 3, 1 and 2, 1, 1. Finally, here are some additional problems and questions. Question 1. Compute the Robinson-Shenstedt correspondent for the permutation 7, 5, 3, 2, 9, 8, 4, 6, 1 from S9. Question 2. Determine an element sigma in S7 whose Robinson-Shenstedt correspondent consists of the following 2 standard Young tableaus of shape 3, 3, 2. The insertion tableau is 1, 2, 3, 4, 5, 6, 7, 8, and the recording tableau is 147, 258, 36. Question 3. Compute the evacuation tableau for the standard Young tableau T of shape 333, which has 126 in the first row, 357 in the second row, and 489 in the third row. Question 4. Determine all partitions lambda for all n, such that the number of standard Young tableaus of shape lambda is equal to 4. And question 5. Determine a tableau T of shape 2 to 1, such that the evacuation tableau for T has 1, 2 in the first row, 3, 5 in the second row, and 4, 6 in the third row. Thank you very much, and this was the last lecture of the course.